everyone. I'm Nurul Hazrina binti Nordin from UMPSD STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome everyone. This is Micro-credential series number 1, Fundamental of IC and HDL Design. The course outcome include to apply hardware description language to design, simulate and verify digital circuits at the register transfer level. The Micro-credential series number 1 consists of 4 main chapters. Chapter number 1, Course Introduction and Overview of IC Design Flow. You will explore the digital design abstraction hierarchy, understanding how design transition from high-level behavioral models down to RTL, gate level, and ultimately physical implementation levels. You will also gain a clear understanding of how the overall workflow of digital IC design. You will gain a historical perspective on the evolution of programmable logic devices, specifically PLA, PAL, and PLDs, to understand how they laid the foundation for modern FPGA-based system. You will also be introduced to design specification and the tools used in this process. Chapter number 2, Introduction to HDL, Verilog. You will learn the fundamentals of Verilog and VHDL, including essential syntax and data types. You will understand the critical differences between simulation and synthesis in HDL, and you will learn how to perform Verilog design entry using the Quartus software. Moving on to chapter number 3, Hardware Description Language Modeling Approaches. Here, you will learn to develop synthesizable Altair designs by applying 3 distinct HDL modeling styles: structural, data flow, and behavioral. You will practice these approaches by modeling basic gates, adders, and multiplexers, while adhering to proper code styles and hierarchical design principles. And finally, chapter number 4, Test benches and simulation for design verification. Here, you will grasp the fundamental concepts of design verification by learning how to construct test benches in Verilog. You will learn to perform functional simulations using Model Sim to verify your digital circuits prior to hardware implementation. And you will learn how to accurately interpret timing diagrams. By mastering these chapters, you will achieve the module's ultimate goal, the ability to design, simulate, and verify both combinatorial and sequential digital circuits at the RTL level using industry-standard tools. Let's move to chapter number 1, Introduction to IC Design Flow. The learning outcomes include digital design abstraction hierarchy, understanding how digital design transitions from high-level behavioral models down to RTL, gate level, and physical implementation levels. The digital integrated circuit and FPGA design flow is a sequential process that transforms a high-level hardware concept into a fully functional physical circuit. This workflow involves several critical stages to ensure the design is correctly synthesized, mapped, and optimized for performance. In stage 1, design entry and verification. This is the first step to describe the desired logical functionality using a hardware description language such as Verilog and VHDL. Designers can write code at different abstraction levels, including structural, data flow, or behavioral modeling. Before moving to the next stage, the design must undergo functional verification, where test benches are written to simulate the code using tools like Model Sim and debug any logical errors to ensure the circuit behaves as expected. In the next stage, step number 2, synthesis. In this stage, synthesis tools like Intel Quartus translates the high-level HDL code into gate-level netlist. The synthesis engine automatically performs logic optimization, minimizing and simplifying redundant logic to reduce the physical area needed. And technology mapping, mapping the abstract logic to the specific hardware resources available on the target FPGA, such as the lookup tables, the LUTs, and flip-flops. Stage 2 also involves Step 3, implementation, fitting, place, and route. This step prepares the synthesized design for development onto the actual physical hardware. It involves mapping and placement, assigning the logic gates, registers and memory block to specific configurable logic block (CLB) inside the FPGA, ensuring they are optimally placed to minimize delays, and routing, establishing the physical electrical connectors and signal pathways between these logic blocks using the FPGA programmable interconnects. And stage number 3, timing analysis and bitstream generation. Here it involves step number 4, timing analysis, where it is performed to verify that the routed design meets all required timing constraints. The tools check for setup time and hold time violation to ensure that data signals arrive at registers within the correct clock cycle limits. If the design fails to meet timing requirement, the designers may need to go back and adjust the HDL code, such as adding pipeline registers to improve the maximum operating frequency. Stage number 3 also involves step 5, bitstream generation. Once the design successfully passes synthesis and timing analysis, the compiler generates a bitstream file for Intel FPGAs. This file contains the completed binary configuration data that instructs the FPGA exactly how to configure its internal hardware connections and logic functions. In the next step, step number 6, FPGA programming and testing. The final step is to load the generated bitstream onto the physical FPGA, such as the DE10 Lite board, using a programming cable like a USB blaster or JTAG interface. Once programmed, the design's real-world functionality can be verified. Engineers may also use real-time debugging tools, such as the logic analyzers, to monitor internal signals and detect errors without needing to reprogram the entire device. When designing a digital system, one of the most crucial decisions an engineer has to make is selecting the right hardware platform. Let's see how microcontrollers, ASICs and FPGA are compared among each other. Let's start with the microcontroller, or sometimes called as MCU. Think of it as your standard reliable workhorse. MCU operate on a fixed instruction set and execute code sequentially, meaning they process one instruction at a time. Because they use a predefined architecture, your development time is very fast, and the chips themselves are inexpensive and easy to mass produce. They also boost lower power consumption, making them a perfect fit for embedded controller system, IoT devices, and automation application. But what if you need maximum uncompromising performance for one specific task? That is where ASICs, or application-specific integrated circuits, comes in. ASICs have fixed hardware tailored exactly to their intended functions. Because the silicon is custom-built for the job, they offer high-performance execution and highly optimized power efficiency. However, this custom fabrication process means they take a long time to develop and are incredibly expensive upfront, though they do become cheap during large-scale production. You will typically find ASICs inside mass-produced consumer electronics and dedicated communication chips. Finally, we arrive at the star of the course, the FPGAs. FPGAs strike an incredible powerful balance. Unlike ASICs, they are highly reconfigurable, meaning you can reprogram the actual hardware connections again and again. And unlike the sequential execution of MCU, FPGA offer high parallel processing, allow them to perform many complex operations simultaneously. While they have a moderate cost and generally consume more power than MCUs, their development time is much shorter than ASICs, since you don't have to wait for a factory to fabricate new chip. Because of this flexibility and speed, FPGAs are the go-to choice for cutting-edge devices like AI and machine learning acceleration, signal processing, cryptography, and networking. Choose an MCU for simple low-power sequential control. Choose ASIC for permanent mass-produced performance, but choose an FPGA when you need high-speed, parallel processing and can adapt and evolve right on your desk. In summary, choose an MCU for simple low-power sequential control. Choose an ASIC for permanent, mass-produced performance, but choose an FPGA when you need high-speed parallel processing that can adapt and evolve right on your desk. In digital IC and FPGA design, the design process flows through a hierarchy of abstraction level. This workflow transforms a high-level conceptual idea down into a physical functioning hardware circuit. Here is a breakdown of the four main design abstraction levels. Behavioral level. This is the highest and the most abstract level of design. At behavioral level, the focus is entirely on the algorithmic functionality of the system, describing what the circuit should do without worrying about the specific hardware or logic gates needed to achieve it. Designers use high-level programming constructs such as if-else statement, case statement, and always block to define the circuit behavior. Moving on to the register transfer level. At this stage, the design becomes more hardware-aware. RTL describes the behavior of the digital circuits in terms of data flowing between hardware registers, memory element like flip-flops, and the combinatorial logic that process the data. This level introduces the concept of clock edge and synchronization. RTL is the primary abstraction level where engineers write synthesizable Verilog to design combinatorial and sequential circuit. The gate level represents the actual hardware structure. During this synthesis stage, software tools like Intel Quartus automatically translates the RTL into a gate level netlist. The abstraction level. At this abstraction level, the design is no longer high-level code. It is a detailed schematics of interconnected physical components, including basic logic gates and or XOR, multiplexers and flip-flop. And finally, the physical level. This is the lowest level of abstraction, where the gate level netlist is physically implemented onto the silicon of the target device, such as the E10-like FPGA. The physical implementation process involves technology mapping, where at this stage, it is about assigning the abstract logic gates to the specific physical hardware resources available on the FPGA, such as the lookup tables and specific registers. Placement, where it involves determining the exact physical location for each logic block on the chip to optimize timing and space. And routing, where it is about establishing the physical electrical pathways and wire connections between all the logic components using the FPGA programmable interconnects. Here you can see the comparison of these abstraction levels versus its hardware specificity. From behavioral, RTL, gate level, and physical layer. PLA, PALs, and PLDs are the historical predecessors to modern FPGAs. They are earlier, simpler form of programmable hardware that eventually evolved into the highly complex FPGA systems used today. Here is how they compare to FPGAs and how they relate to logic gates. PLD, PLA, and PAL are designed to implement digital logic, but they do it in different ways. PLD stands for Programmable Logic Device. This is a broad umbrella term for the early programmable chips. PLA, Programmable Logic Array. This device consisted of an array of physical AND gates connected to an array of physical OR gates. In a PLA, the interconnections to both the AND gates and the OR gates were programmable, allowing users to build custom combinatorial logic functions. On the other hand, PAL, Programmable Array Logic. This was a streamlined version of the PLA. It features a programmable array of AND gates, but the OR gate interconnections were fixed. This made them less flexible than PLAs, but faster and easier to manufacture. While PLA and PALs physically routed signals through arrays of basic logic gates, modern FPGA approach logic design very differently and are vastly more powerful. For example, you can see here, FPGA is equipped with lookup tables instead of simple gates. Instead of relying on simple arrays of AND OR gates, FPGAs use configurable logic blocks, CLBs. Inside these CLBs are lookup tables, which are small memory elements that store pre-computed logic function values. Lookup tables completely replace traditional logic gates by simply mapping given inputs to their corresponding programmed output. Early PLDs were generally limited to simple combinational logic. FPGA, on the other hand, paired their lookup tables with built-in flip-flops and registers for complex sequential logic. FPGAs also introduced advanced internal components that PLDs lack, such as block RAM for data storage and dedicated digital signal processing blocks for high-speed arithmetic. While PAL and PLAs physically routed signals through an array of basic logic gates, modern FPGAs approach logic gates designed very differently and are vastly more powerful. While PLAs and PALs physically routed signals through an array of basic logic gates, modern FPGAs approach logic gates very differently and are vastly more powerful. Instead of relying on simple array of AND and OR gates, FPGA uses configurable logic blocks, CLBs. Inside these CLBs are lookup tables, which are small memory elements that store pre-computed logic functions values. Lookup tables completely replaced traditional logic gates by simply mapping given inputs to their corresponding programmed output. Early PLDs were generally limited to simple combinational logic. FPGAs, on the other hand, pair their lookup tables with built-in flip-flops and registers for complex sequential logic. FPGAs also include advanced internal components that PLDs lack, such as block RAM for data storage and dedicated digital signal processing blocks for high-speed arithmetic. Because FPGAs use lookup tables and highly programmable interconnects, they are much more highly reconfigurable than early PLDs, making them suitable for massive parallel processing tasks like AI acceleration, cryptography, and complex networking. FPGAs are incredibly powerful and highly flexible, but what actually makes them tick? Today, we are pulling back the curtain to explore the internal architecture of a field programmable gate array. At the heart of FPGA, arranged in a massive grid, are the configurable logic blocks, CLBs. Think of these as the core processing elements of the chip. They are responsible for implementing all of your digital logic functions. If we zoom inside a single CLB, we find three critical components. First, its lookup table. Instead of using hardwired traditional logic gates, lookup tables act like small memory elements that store pre-computed logic values, mapping your given inputs directly to their correct outputs. Next, we have the flip-flop and registers, which handle data storage and keep your sequential logic perfectly synchronized to the clock. Finally, we have the multiplexers that help select and route different input signals within the block. But how do all these separate blocks talk to each other? That is the job of the programmable routing and interconnects. This is a massive dynamic network of wires that establishes physical electrical pathways between different logic elements. Depending on your code, this routing matrix physically configure itself to connect your circuits exactly how you design it. Beyond the standard logic, modern FPGAs also pack specialized hardware. You will find block RAM dedicated to on-chip data storage and digital signal processing or DSP blocks, which contain built-in hardware multipliers for high-speed arithmetic used in AI and cryptography. Finally, you will find block RAM dedicated to on-chip data storage and digital signal processing or DSP blocks, which contain built-in hardware multipliers for high-speed arithmetic use in AI and cryptography. Finally, surrounding everything are the I/O banks that interface your internal logic with external components like the switches, sensors, and displays on your DE10 light board. By combining adaptable CLBs, specialized hardware, and a fully programmable routing network, the FPGA gives you a blank canvas to build virtually any digital system you can imagine. Before we fully appreciate modern FPGA technology, it is important to understand how programmable logic started. Earlier programmable devices such as programmable logic arrays and programmable array logic were used to implement digital logic functions in hardware. Both PLA and PAL are based on a simple idea: implementing logic using two levels, AND plane to generate product terms and OR plane to combine those terms into final outputs. The key difference between them lies in flexibility. In a PLA, both the AND and OR arrays are programmable, whereas in PAL, only the AND array is programmable, while the OR array is fixed. This means PLA is more flexible, but also more complex and slower compared to PAL. These devices were widely used before FPGAs become dominant, and they represent the early evolution of programmable hardware. In general, there are two enabling concepts in PLD's implementation: shared product terms and multiple input functions. Let's look in detail in the next upcoming slides. Now let's look at how these programmable logic devices actually work. The first concept, implementing multiple input functions using PLA. Say for example, we are given the following functions: F1 equals to A, B, C, F2 equals to A or B or C, F3 equals to A bar dot B bar dot C bar, F4 equals to A bar or B bar or C bar, F5 equals to A exclusive or B exclusive or C, and F6 equals to A exclusive nor B exclusive nor C. And we are asked to implement them using a PLA with 8 AND gates and 5 OR gates. Here, the PLA allows us to generate different combinations of input in the AND gate and then combine them in the OR plane. However, you will notice something important. Some functions are simple, like the AND and OR. Some are more complex, like exclusive OR, exclusive NOR. Exclusive OR and exclusive NOR requires multiple product terms. This means the number of AND gates becomes a limitation. The number of OR inputs also limits what we can implement. So, even though PLA is flexible, it is still constrained by fixed number of product terms, limited scalability, and increasing complexity for larger design. So how do we proceed from here? Well, instead of thinking in terms of individual Boolean expressions, let's approach this using a lookup table concept. We now have three inputs, A, B, and C. With three variables, we know that there are 2 to the power of 3, equivalent to 8 possible input combinations. So what I've done here is construct a truth table listing all possible combinations of A, B, and C from 000 until 111. So the next step, for each of these 8 input combinations, we evaluate the output for all the functions, as mentioned earlier. F1 being A.B.C, F2 being A or B or C, until F6 being A exclusive nor B exclusive nor C. So essentially, for every row in the table, we are defining what each output should be. At this point, what we have is essentially a lookup table. where inputs are addressed and output are stored values. Now, how does this relate to a PLA? In PLA, the AND plane generates all possible input of combination. We call this as minterm, whereas the OR plane selects which combination contribute to each output. Now, how does this relate to a PLA? In the PLA, the AND plane generates all possible input combinations. We call this as minterms. The OR plane selects which combinations contribute to each output. Since we have 3 inputs, we can now generate up to 8 minterms. Matches our 8 AND gates situation. So each AND gate corresponds to one row in the truth table. As we can see here, the first one represents A bar, B bar, C bar. The second one represents A bar, B bar, and C. And until the end, the last represents A, B, and C. Now comes the important part, the OR plane. For each function, we look at the truth table, identify which row produce output 1. Now comes the important part, the OR plane. For each function, we look at the truth table, identify which row produces the output 1. Then connect those corresponding AND output to the OR gate, such as shown here. These are corresponding to the inputs, whereas these are corresponding to the outputs. So effectively, each output function is formed by summing selected minterms. Take note that in this situation, the function of F5 is equivalent to F6, hence the following items. This is exactly how the PLA implements logic. Now let's have a look at the second concept, shared product terms. We are given several logic functions, for example as shown here, function 0, F0, F1, F2 and F3. If you observe carefully, some product terms are reused across multiple functions. For example, B bar, C bar appears in F0. For example, B bar, C bar appears in F0 and F2, whereas A.B appears in F1 and F2, and A appears in F0 and F3. In a PLA, we can compute these shared product items once in the AND plane and then connect them to multiple OR gates. This is called sharing product terms, and it allows us to reduce hardware usage, improve efficiency, and avoid recomputation. So instead of building separate logics for each function, we reuse intermediate results. This is one of the key strengths of PLA compared to the fixed logic design. Another example is as shown here. The PLA consists of an array of only 7 AND gates, while the functions given contain 9 expressions. Hence, the Boolean expression has to be rearranged using Boolean identity and axioms as follows. The rearranged Boolean equation now has 7 expressions and could fit the given template nicely. However, PLA's and PAL's chip are limited to fairly modest size, typically supporting a combined number of inputs plus output of not more than 32 due to the limitation of the input and output size. Modern electronics application requires more input and output and function. Hence, FPGA, the Field Programmable Gate Array, is introduced. So, before moving to the FPGA chapter, let's have a look what is the internal build-up of the gate. Logic gates are primarily implemented using diodes or transistors, acting as electronic switches, but can also be constructed using vacuum tubes, electromagnetic relays, fluidic logic, pneumatic logic, optics, molecules, or even mechanical elements such as shown here. With amplification, logic gates can be cascaded in the same way that Boolean function can be composed, allowing the construction of physical model of all Boolean logic, and therefore all the algorithms and mathematics that can be described with Boolean logic. Modern digital systems are designed in CMOS technology. CMOS stands for metal oxide on semiconductor. C is for complementary because there are both normally open and normally closed switch. MOS transistors act as voltage control switches similar, though easier to work with than relays. MOS transistors have three terminals: drain, gate, and source. They act as switches in the following way. If the voltage at the gate terminal is higher or lower than the source terminal, then a conducting path will be established between the drain and the source terminal. An example of a switch is shown here. So, when a 1 is placed at X, the N-channel MOS is closed, hence giving the output of 0. This function resembles the inverter. Likewise, the switches could be arranged in parallel form. And form different gate functions as follows. The speed of CMOS network depends on charging and discharging of voltage on wires and gates of transistors. Capacitors hold charge capacitance is at gates of transistors and wire material. Resistors slow movement of electrons resistance mostly due to transistors. The speed of CMOS network depends on charging and discharging of voltages on wires and gates of transistors. Capacitors hold charge capacitance is at gates of transistors and wire material. Resistors slow movement of electrons resistance mostly due to transistors.
Hello, hi. I am Nurul Hazrina binti Nordin from UMTSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to this presentation on Chapter 2 entitled Verilog and FPGA Design. In this session, we will cover the basics of Verilog syntax, writing modules, setting up quarters prime, coding principles, test benches, and simulation techniques. By the end of this session, you will have a solid understanding of Verilog fundamentals and how to apply them in FPGA development. As we dive into the world of digital design, we need to talk about the languages we use to build this system. Hardware Description Languages or HDLs. But before we write a single line of code, we need to address a critical mindset shift: hardware programming versus software programming. Hardware programming is fundamentally different from traditional software programming. At the first glance, an HDL like Verilog might look incredibly familiar. It features a concise C-like syntax that makes it very approachable if you already know procedural programming. You will use standard construct like if-else and case statement. But don't be fooled. Unlike traditional programming languages, HDL are not writing a sequence of instructions, but a processor to execute. Instead, you are using code to describe the actual physical architecture of a digital circuit. To truly understand the shift from software to hardware, let's look at this example, a simple 4-bit counter with an enable switch. It's the perfect case study in how these two worlds diverge. On the software side, the counter lives within the loop. The processor must visit the increment line, execute it, and then move to the next instruction. If the processor is busy elsewhere, the counter stops. In software, the counter is a process. It only happens when the CPU gives its attention. Now, let's look at the Verilog side. Here, the counter isn't a list of instructions. It is a physical description. When you write this in HDL, you are telling the FPGA to wire up 4 specific flip-flops and an adder circuit. In hardware, the counter doesn't loop or wait for its turn. It exists as a dedicated piece of silicon. The moment the clock edges hit, the logic transitions instantly and simultaneously. While a software loops wait in line, your hardware circuit is always on, reacting in real time to the clock and the enable switch. This is the power of the FPGA. You aren't sharing a processor's time, you are creating a custom machine where every components work in parallel at the speed of light. HDLs are entirely different from traditional software programming. They allow engineers to describe and synthesize actual digital circuits. Today, we are looking into the two industry heavyweight, Verilog versus VHDL. If you look at Verilog, you will notice it has a concise C-like syntax because it is easy to use and event-driven. It is incredibly popular in the commercial industry and is the go-to choice for rapid prototyping. On the other hand, VHDL features a more verbose, Pascal or Ada-like syntax. It enforces strong typing and explicit data types. Because of this rigor, VHDL is preferred language for high reliability and safety critical applications, such as aerospace and automotive systems. In this course, we will focus our energy on mastering Verilog and digital system designs. You have written your Verilog code, but how does it become real hardware? It requires two critical distinct steps. We call this as simulation and synthesis. First comes simulation. Before your code ever touches an FPGA, you must verify that it is functionally correct. Using tools like Model Sim, you will write a test bench to apply simulated inputs to your design. By analyzing the resulting waveforms, you can catch logic errors, check syntax transitions, and debug your circuit in a safe virtual environment. Once your simulation proves the logic is sound, you move to synthesis. This is the heavy lifting. The synthesis tool, like Intel's Quartus Prime, translate your abstract Verilog code into a gate-level netlist. It parses the code, optimizes the logic to remove dead, and maps your design directly onto physical primitive of the FPGA, like lookup tables and flip-flop. In short, simulation proves your ideas work, and synthesis turns that idea into actual hardware. Now that we have chosen Verilog to proceed, let's explore its essential building blocks. Every Verilog design is encapsulated inside a module and ends with an end module state. Within these modules, data flows into specific variable types. The two most common are wire and registers. A wire is used for continuous assignment. Think of it as a physical wire connecting logic gates. A reg or registers is used for procedural assignment inside always block to hold values. You also have types like integer, real, and logic. To manipulate this data, Verilog is packed with operators. You have your standard arithmetic operator for mathematics, logical operators for conditioned, and bitwise and shift operators to manipulate signals down to the individual bit level. Combining these data types and operators give you the power to model any digital behavior. Now let's go through the general steps in the FPGA design flow. We begin with the specification phase. This is where we define the system requirement, including functionality, performance, and constraint. It sets the foundation for the entire design process. Next, we move to design entry. In these steps, we write the circuits designed using hardware description language such as the Verilog. This allows us to describe the logic behavior at the register transfer level. Once the design is written, we perform a functional simulation. This is a critical step where we verify the logic works as expected before moving to the hardware implementation. We use software tools like Model Sim to simulate the behavior of our design. After verification, we proceed to synthesis. Here, the HDL code is compiled and translated into gate-level netlist. The netlist represents the logic gates and their connections that will be mapped onto the FPGA hardware. Following synthesis, we move into implementation, which involves placement and routing. The design is mapped onto the FPGA's logic element, and interconnections are established to optimize performance. Once the placement and routing are completed, we conduct timing analysis. This step ensures that the circuits meets speed requirement and the signals propagate correctly within the FPGA. We analyze setup and hold times to prevent timing violations. Finally, we reach the programming and testing phase. The synthesized and optimized design is programmed onto the FPGA hardware. We then conduct real-time testing to verify functionality and debug any remaining issues. By following this structured design flow, we ensure that our FPGA-based system is functional, efficient, and optimized for performance. So the IC design process consists of several key stages, from defining system specification into final testing and validation. Let's explore each stage of this Altera FPGA design flow in detail. First, we define the system specification. These include requirements like power consumption, clock speed, and overall functionality. For example, in a Pico satellite like Lilex 5 onboard computer (OBC), the system must process sensor data efficiently and communicate via LoRa wireless transmission. These steps ensure we understand the constraints and the objective before we begin designing. Next, we define the system's architecture. This stage focuses on identifying functional blocks such as arithmetic logic unit, memory units, and data interfaces. For instance, in an FPGA-based DE10-like Pico satellite system, we may need separate blocks for data acquisition, processing, and transmission. This stage helps create a blueprint of how the system will function. Now we move into register transfer level, RTL, where we write the system's logic using hardware description language like Verilog or VHDL. For example, if we want to control an LED into Pico satellite onboard controller, we write Verilog modules that turn the LED on or off based on sensors input. This stage represents the actual coding of the hardware design. Once the RTL design is complete, we need to verify its functionality. Using simulation tools like Model Sims or Quarter Sprint software. For example, before deploying sensors processing logic on an FPGA, we simulate its behavior to check for errors. This step helps catch logic flaws early before moving forward. In the logic synthesis stage, the HDL code is converted into gate-level representation that can be implemented on the FPGA. Using tools like Quarter Sprint, we translate the Verilog code into actual logic gates. For example, the system ensures that the LED module is correctly mapped onto the FPGA resources like the logic elements and flip-flop. Then we move into timing analysis and optimization. Timing is critical in digital design. At this stage, we perform static timing analysis to ensure signal transitions occurs within defined constraint. For example, in the LoRa communication systems, data transmissions must be synchronized without exceeding delay limits. By optimizing clock path and signal delays, we prevent timing violations that can affect system performance. Now that the logic is synthesized, we need to map it onto the physical FPGA hardware. This involves assigning FPGA pins for various components. For example, we must carefully allocate I/O pins for the MPU6050 sensors, LoRa transceivers, and LED in the DE10-like Pico satellite project. This ensures correct physical connections and avoid signal conflicts. Timing is critical in digital design. At this stage, we perform static timing analysis to ensure signal transitions occurs within defined constraint. For example, in the LoRa communication system, data transmissions must be synchronized without exceeding delay limits. By optimizing clock path and signal delays, we prevent timing violations that can affect system performance. Now that the logic is synthesized, we need to map it onto the physical FPGA hardware. This involves assigning FPGA pins for various components. For example, we must carefully allocate I/O pins for the MPU6050 sensors, LoRa transceivers, LEDs in the DE10-like Lilex project. This ensures correct physical connections and avoid signal conflicts. Once the design is finalized, we generate bitstream file and load it onto the FPGA. We verify the FPGA system through test benches and real-world scenarios. For example, we test our Lilex 5 handles sensor data in space-like condition. This ensures reliability and performance before deployment in an actual satellite mission.
Hello, hi. I am Nurul from UMTSP STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to Chapter 3, HDL Modeling Approaches. Verilog is a hardware description language used for designing digital circuits and FPGA programming. It follows a structured syntax similar to programming languages like C, but is specialized for hardware modeling. A Verilog module defines the circuit behavior. Ports allow communication between modules, and data types like wire and register help to define signal properties. This is an example of a top module with input A and B and output as out. Verilog encompasses a wide range of concepts used to design, simulate, and synthesize digital hardware. Unlike traditional software, Verilog describes concurrent hardware architecture. Here are the core concepts of Verilog HDL. Verilog signals can have 4 basic values: 0 for logic 0 or false, 1 for logic 1 or true, Z for high impedance state, and X for unknown value. The net group, it represents physical wire connections between hardware components. The most common type is wire, which is used as the output for continuous assignment and to connect different modules. Whereas register store data for outputs in procedural block. It is typically controlled by flip-flop. Numbers in Verilog can be sized or unsized, defined by their bit length, base, like binary, hex, decimal, octal, and values. To truly master Verilog, you must understand that there is more than one way to describe a digital circuit. Depending on the complexity of your design, you will choose between 3 primary modeling styles: behavioral, data flow, or structural. Let's look at a simple NOR gate to see how these differ between one to another. First, we have the structural modeling technique, also known as gate level modeling. This is the lowest level of abstraction, acting much like a physical wiring schematic. Notice here that we use the word NOR. In Verilog, this is a color-coded reserved word or primitive. The software inherently understands what a NOR gate is. We are instantiating a physical gate and wiring X and Y to its input. It is the closest representation to the actual silicon. Next is the data flow modeling. This is a mid-level approach where we use Boolean expressions to describe how data flows through the circuit. For our NOR gate, we use the assign statement. We simply defined the output M as the logical inverse of X or Y. This is highly efficient for combinatorial logic because it is concise and directly reflects the mathematical truth of the device. And finally, we have our highest level of abstraction, the behavioral modeling technique. Here, we aren't thinking about gates or wires. We are describing the logic of the system using procedural constructs. In this NOR gate example, we use an always block. We tell the hardware, look at the input X and Y. If both are zeros, the output M should be 1. Otherwise, it is 0. It reads almost like software algorithm, making it perfect for describing complex system behaviors without getting bogged down in the circuit details. Now, you might ask, if all the 3 describes the same NOR gate, why does it matter? Well, while these models look different to us, the synthesis tool will eventually translate all of them into a single gate level netlist. This netlist is the truth of the hardware, the actual arrangement of transistors and wires on your FPGA. So, which one do you choose? Well, gate level modeling is incredibly efficient and gives you total control over the hardware. But as your designs grow, it becomes impossible to wire thousands of gates by hand. That is why, for complex high-level system, behavioral modeling is the way to go. It allows you to design at the speed of thought while letting the synthesis tool handle the heavy lifting of physical implementation. Now let's move into the procedural blocks in Verilog. Hardware operates concurrently, but within Verilog, you can write procedural statement executed in sequence. These must be encapsulated in specific blocks, such as shown here. There are two main blocks. The always block. It represents an abstract circuit part that runs continuously in a loop, triggered by a sensitivity list. It is a list of signals that activate the blocks when they change. It is used to synthesize both combinatorial and sequential logic. And secondly, the initial block executes only once at the very beginning of the simulation. It is primarily used in test benches to apply initial testing stimuli and cannot generally be synthesized into hardware. There are also blocking versus non-blocking assignments. When writing procedural code inside an always block, Verilog uses two distinct assignment operators. We call this as blocking, typically represented by the equal sign. It evaluates and assigns the value immediately, blocking the next statement until it finishes. It acts sequentially like C programming and is used strictly for combinatorial circuits. On the other hand, the non-blocking statement. It evaluates all expressions at the start of a time step, but differ the actual assignment to the variable until the end of the time step. This allows multiple assignments to happen concurrently without race conditions and is used strictly for sequential circuits like flip-flop and registers. Verilog includes a rich set of operators to manipulate data. We have the arithmetic operators, the addition, subtraction, multiplication, division, bitwise and logical operators, basically used to manipulate signal bit by bit, whereas logical operators to evaluate whole expressions as simple true or false. We have the relational and equality, evaluate conditions, returning the value true or false. There is also shift operators, where it moves bits left or right, and concatenation combines multiple smaller signals into larger bus. There is also conditional operator, where it acts as a simplified if-else routing structure, commonly inferring a multiplexer. Now, take note, in Verilog, there is combinational and sequential logic at the RTL level. Specifically for RTL design, circuits are described in a combinational logic and sequential logic. Combinational logics are circuits where the outputs depend only on the current inputs. For example, adders, multiplexers, and decoders. It is modeled using assigned statements or always block with blocking assignments. On the other hand, sequential logic are circuits that contains memory or internal state, meaning the output depends on both current input and previous history. They are driven by clock signals, such as the post-edge clock or negative edge clock, and modeled using always blocks with non-blocking assignments to infer D flip-flops and registers. We shall cover this in detail in the subtopic of finite state machines or FSM.
Hello, hi. I am Nurul Nordin from UMTHD STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to chapter number 4, Test Benches and Simulation for Design Verification. Before you ever program a physical FPGA, you must prove that your logic actually works. How do we do that? Through simulations. Today, we are looking at how to verify a digital circuit using Verilog Test Bench. Let's dive in. Think of a test bench as a virtual lab environment. It is a special Verilog module designed to do three things: generate virtual input signals, the stimulus, feed them into your hardware design, the device under test or typically labeled as DUT, and observe the results, the output checker. Unlike standard hardware modules, test benches have no physical input or output ports. Everything happens internally within the simulation. Let's look at an example of using a test bench on a full adder circuit. To set up the test bench, we first declare our signals. We use reg for our inputs, like the A, B, and C in, because we need to procedurally apply and hold these values during the test. For the outputs, the sum and C out, we use wires, because they will be continuously driven by the full adder module. Next, we physically connect our virtual lab to the circuit. This is called instantiation. We instantiate a full adder module, passing our test signals into its ports. Now, the device under test is wired up and ready to go. To actually run the test, we use an initial block. This block executes sequentially, just once, at the very start of the simulation. Inside, we set up a monitor task. This is a brilliant debugging tool that automatically prints a message to the console every single time any of our signals change state. Finally, we apply our test vectors. We set A as 0, B as 0, C in as 0, and then we add hashtag 10. This hashtag 10 introduces a 10-unit time delay. By applying different ones and zeros and stepping forward in time, we create a sequence of test cases. When we are both done, we call finish to stop the simulation. By loading this test bench into a simulation tool like Model Sim, we can view the resulting waveforms, verify our timing, and catch logic errors before they ever touch the hardware. Simulation isn't just an extra step. It is the secret to successful digital design. Once we run our test bench in Model Sim, we move from looking at code to looking at the functional simulation waveform. This is where we verify our logic actually behaves as expected. Let's analyze the results for a standard 2-input AND gate. On the far left, you see our signal names. A and B are our inputs and Y is our output. This corresponds exactly to the ports we define in our Verilog modules. The horizontal axis represents time, usually measured in nanoseconds. As we move from left to right, we are watching the history of our circuit's behavior unfold. Look closely at the lines themselves. In digital system, we live in a binary world. When a signal is high at the top of its row, it represents logic 1. When it drops to the low position, it represents logic 0. In the first segment, we notice that input A is high, but input B is low. Because an AND gate requires both inputs to be high to produce a result, our output Y remains at 0. We can see this clearly. The Y line stays flat at the bottom. Now watch what happens as time progresses. The moment of both A and B cross into the high position. Look at the output Y. Instantly, it transits to logic 1. This vertical change confirms our AND gate is functioning correctly. This is the power of Model Sim. It allows you to see the invisible by comparing the ideal timing of your inputs against the resulting output. You can catch errors in your logic before you ever spend time compiling your design for the DE10 light board. If the waveform looks correct here, you are ready to move toward physical synthesis. Now that we have described our hardware, we need a way to test it. In Verilog, we use two primary procedural blocks to drive our simulation: the initial block and the always block. Think the initial block as your setup routine. It runs exactly once, starting at the very beginning of the simulation. We normally term this as time 0. This is where you initialize your input. apply specific test vectors, and tell the simulation when to stop. Because it only runs once, it is perfect for defining a specific sequence of events. The always block, however, is the heartbeat of your simulation. As the name suggests, it runs continuously throughout the entire simulation sessions. It is triggered by event changes, most commonly the edges of a clock signal. In a test bench, we often use an always block to generate a repeating clock pulse, ensuring our synchronous logic has a signal to react to. But how do we actually see what's happening inside? Since we can't look at a physical wire with a multimeter during simulation, we use Verilog system tasks to print debugging outputs. First, we have the display. This works much like a print statement in C++. It prints a message to the console at a specific simulation step. It's a snapshot in time, perfect for checking the state of a signal at exact moment. If you want to track a signal over time without writing dozens of display statements, use monitor. This task is more intelligent. It stays active and automatically prints an update to the console every single time the value of a monitored signal changes. It's like having a live log of your circuit's activity. Finally, the most detailed analysis, we use dump file. This command tells the simulator to record every signal transition into value change dump or a .vcd file. You will load into Model Sim to view your functional waveforms. By looking at these waveforms, you can see the timing relationships between your signals and verify that your design behaves exactly as intended before you ever commit it to the FPGA hardware.